recording going. All right, so there are several things we want to talk about today. First, brief update on things. I am most of the way through scanning in all the midterms. It's taking a little longer than I thought because my phone is old and it keeps taking blurry pictures and I have to retake things. Um, so I'm hoping I will have that done probably this afternoon. I'm guessing I got about, from how things have been going, about another hour or so of photo taking, checking, retaking, naming things, and then um, once I've got them all done, I'm putting them basically with people's names on them, and then um, I'm thinking I can make a special discussion thing for each person. I'll have to see how that will work to distribute them. I'm gonna upload them into Canvas so that you can have one stop where you can kind of go and look. I might even make it as its own little assignment, make the midterm and just call it midterm extra credit, and then you can respond to it. I'll see if I can do it that way. Um, I do have, the one thing I have to do is make sure that nobody's can see anybody else's midterms, basically for your privacy issues. So that will hopefully be done today. Let's see. The other thing that was mentioned was that an issue people have been having in labs, which kind of relates to what we're talking on counters today. Um, so people are having problems with getting a counter to counter, getting weird flickering and stuff. That is, so it was just mentioned to me a couple days ago, and that is completely caused by basically using the clock input. And the clock inputs is a little bit different on the way Xilinx sets up their FPGAs. Um, Maybe I'll mention it right now when they're just to go on. So this will relate to a subject that's a little bit later in the course. I've also put up course modules, and I put on each of the pages for it the day I think I'm going to cover that material. So assuming we can kind of get through things, so that way you can kind of look ahead and plan what's going to happen for each one. And I'll as soon as it takes about a day for the videos from these to become ready. So sometime early tomorrow morning, this video will become ready, and then I'll download it and then upload it back again. It sounds retarded, but it's the only way I can get out of WebEx and into Canvas. They have no way to directly copy, and then I can link it inside. So it'll take about a day and a half for each one of those to go through, but then the video will be up and available. Anyway, so there's kind of, when you consider your FPGAs that you're working on, FPGAs, particularly Xilinx style, does these combinational logic blocks, or CLBs. Each of these logic blocks inside them, just as a note, has basically a lookup table. So this is what does your actual logic. It's got 4 addresses that tell it which one of the lines. 4 addresses gives you 16 inputs. And so these are numbered from 0 through 15. And the 4 bits of logic that come in pick which line you're on. So this is kind of like when we literally make a logic table and we write all the binary combinations. I'm just writing them in decimal to save myself time. But if you want to just think of them in binary, you've got 4 zeros through 4 ones. That's the basic of their lookup table. And then for each one of these, they've got what the outputs are. And you can program what these outputs are. So this style of thing where you go in is actually, and we'll talk about this later in more detail, but this style is called a ROM, because basically your inputs become addresses and your outputs become the memory that's stored at that location. So they're called lookup tables or ROMs, based off the old read-only memory. And when you're programming your thing, what they do is they figure out what your logic would do for that particular address, and it just stores it as a memory location. So this is the way that your logic is actually implemented. It basically takes all the things, calculates all combinations, finds the uses the inputs as an address, and stores them all. Right. The output of this logic table, which we'll say is another 4 bits, it'll vary by the particular construction. Um, remember we have the ability to invert, so they usually go into an exclusive OR, and the other bit is typically set to 0, but it could be 0 or 1 for invert or not invert. That's another thing that you can program. Remember how we had sum of products and product of sums, but we also had negated sum of products and negated product of sums. This bit, if it's 0, it does sum of products, sum of product of sums style, or you can just flip that and it flips everything in the chart. That's another parameter that's in, and then this on the simplest one goes into a D flip-flop or a series of D flip-flops since it's 4 bits. So there'd be 4 of these D flip-flops that go in. I'm just going to show that by just a single one here. And then it's understood since it's 4 in and 4 out, there must be 4 of them here. Now, if you do this, this has its own clock. And if you notice, the clock is not accessible by the logic. Only the D input is accessible. And this is really the kind of the key to what's going on here. This clock has to come from something that is registered as a clock input. Now, this combinational logic block, there's actually a whole bunch of different routings that are potential inputs. So these are wires, and they can be tapped to, do I want to read this wire for inputs? So they can select. And then you can also route. So there's routing, which selects the different areas. And at each corner, there's a route. And we'll do this in a lot more detail when we talk about it. There's lots of combinational logic blocks and wires everywhere. And at every corner, there's a route block. And it just keeps on going like this. They just set up this giant array of these logic blocks connected by routing arrays all the way through. So you end up with this type of a setup, and the inputs come in here and the outputs go here, and you can route the signals however you want to route them. So regular logic signals are all part of this, and this is on one layer on the chip. But there's also layers above it. Since it's a multi-layer device, there's also a clocking layer. This is one layer that has all the normal signal routing and all the logic. There's a separate layer that has the clocking. And it doesn't have a lot of logic on it. So that it's really easy to get the signals to where they need to go. Because remember, timing, this is getting small. Don't worry about the particulars in here, right? The particulars in here we will cover in detail, and I'll draw it quite a bit bigger. This is actually, I'm just borrowing an idea from a future chapter. I don't know which it is. It's either 7 or 8, where they talk about how these go in. And the real thing to understand from this picture is that there is a layer that has logic and routing. So all of the logic and the routing are here. These combinational logic blocks have basically a simple way to do logic in them. So this is kind of the logic part. And then there's a memory. So each one of these has logic and then a clocked input. And that clocked input connects to a different layer. But it's a layer that your logical signals can't get to. They're completely separate. Does that much make sense? Because that's really what I want you to get from this picture. I'm adding more detail just because I can't not add more detail. It's just who I am. But the big thing is just to understand that part. Does it make sense? Logic, both and signal routing on one layer, clocking on another. And then this up here is a detail of what's in here. But really the big thing you need to understand about what's inside here is there's a front section of this. So inside any one of these, there's the first part that does the logic, and the second part is memory. And that memory just holds the output. And the memory for its clocking gets its signals from this clocking layer. And the clocking layer is really not jumbled up with lots of stuff. So it's very easy to send the clock signals. Because if your clock ever gets slowed down too much, you can have a problem, right? Because we need to say that, you know, everything's being measured at this one point. Well, if your clock isn't accurate, right, then it kind of defeats the purpose of having a clock. So therefore, we don't want to have a clock going through some crazy roundabout route. You know, think of it this way. Imagine that, you know, the roads in a town are your wires on the system, and the cars driving around are kind of the signals or the data you're trying to send. The most important signal you've got to send to make everything work is going to be your clock signal. Think of that like an ambulance. So yeah, I understand some of these things, the details are not as important, and I will actually cover everything that's in here. You'll see this kind of general shape where there's a block with some names in them and wires. You'll see all that stuff in, I think it's about a week. The name of the lesson, if you look up the module, will be something like, let's see, I think it's called ROMs, PLAs, and FPGAs. When I'll talk about how each of those are kind of built, and therefore how we can turn what we're doing in class into those type of things, which is done automatically for you by Vivado, but you know, you want to at least understand what's going on in the process. And the reason why it's helpful to understand the process in the memory box. Oh, over here, this part. Yeah, I can draw that a little bigger. It's again, it's not huge. So if you just think of this first part as a logic table, and the logic table outputs and goes to a D flip-flop, and the clock input is coming from the clocking layer. But the logic is coming from and returning back to the logic layer. Right? That's the whole real trick here. So now imagine for a sec, you take a logic signal, something you generate here, but you try to input it to a clock. There's no way to route this signal to the clocking layer. You see the separation between them? And the reason is the system doesn't know how to time this. Well, it knows how to time it. It knows how to time it as a logic signal. It can't time it precisely as a clock. So therefore, it doesn't want you to take these and put them over here. So if you attempt to build an FPGA design that goes into a clock from one of its logic signals, now you can mention different clocks. There are ways to get different clocks. This clocking layer can have like 16 different clocks, and you can set them different and stuff like that. But this has to be set in the constraints file. You can set what clocks there are and how they're timed and things like that, but it's a fixed timing between them, right? So we'll often do what are called clocking blocks and all kinds of other stuff to set these constraint files. But taking logic and putting it into here, FPGAs don't have a way to do that, right? So since it doesn't have a way to get this signal to here, but you told it to, what it has to do is to fake, instead of using the actual D flip-flop that's built into the system and has good timing to it, it's going to attempt to build a flip-flop by feeding logic tables back into each other. Okay? The second it takes logic tables and feeds them back into each other, that's a really inefficient way to do. So it's going to take a bunch of these logic blocks. So it'll take a big section, but then it's got to route these signals between stuff. And you're now doing a bunch of routing to build the logic, and then you also have to pull in the signals to then use the logic. So you get a big mess happening in one area. When you get that huge mess happening in one area, it kind of expands it out to deal with that, which means the routes become longer and the timing becomes worse. So the worse the timing becomes, because it can't do it efficiently, because the clock input is being used for a logic signal, essentially the design grows big enough that the timing constraints aren't met. Once the timing constraints get into problems like that and you're feeding logic back into logic without being able to properly use this, what you'll get stored in these locations will be intermediary results. Because remember how it could take a couple times till the flip-flop settled its value? Well, that means in the meantime, it could be turning on and off. You've missed the things, so it can become metastable. You can get, errors of type 1. All the protections that are normally here get blown away because that's not what's supposed to be used, right? You should only ever use a designated clock signal to time a D flip-flop inside an FPGA, because that's just a requirement of how the system is built. If you've got an individual component, you can deal with it. It's still dangerous, but you can do it and you can do it better. The FPGA just has no way to do it. So it has to fake it and it just becomes really ugly. Therefore, what happens is the longer the route, and now if you consider what you guys were doing, I believe you were doing counters, and your counter, when it's going in, the smaller digits change faster, so they're going to have shorter routes. The larger digits use the earlier digits plus themselves, so they've got a really long loop. So the further you get, the bigger the digit, the more these errors will get exacerbated, which means the more the digits are going to get weird values and flicker and do stuff like that. So when you're doing any type of a logic design on an FPGA, please, 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 please do not use the clock with the logic signal. Don't use reset with the logic signal either. The resets also come in under a special case. So resets are another one of those kind of cases that's in. So when we do that, pos edge clock, neg edge reset type of a thing, those signals, when you actually simulation, it doesn't matter, but it does matter when you go to actual build. When you go to build, those should be identified as those special signals because they go to a different layer. Both clocking and resets and things like that get they're high priority. So they're kind of like that ambulance on the street, right? We want them to have the quick access to get where they're going. And we do that by building them their own special roads. So they get like the highways and everybody else has to go through city streets. So that's kind of the difference between them. And we don't want to have regular ones on there because we have no way to just divert the traffic. Okay, does that make sense? Yes. Okay, so that should help at least understand what's going on the Logic Lab. And I was told they sent a thing to flip that inside the manual. So sorry that the manual had design. That design, like I said, it would technically work for a individual components, but it is not safe at all for the type we're dealing with. And we'll take a look. Some of the standard ones we're going to do, we'll look at a ripple counter. It has this that same type of a design. Ripple counters would not be a good counter to build on an FPGA. And I would also add that ripple counters and any of these other ones that are kind of more asynchronous, the clock is being used for something other than clocking, tend to be very dangerous on the build. You tend to be more prone to errors, um, beyond just the FPGA type errors. So I'm just switching side because otherwise I'm standing in one spot too long and that's just not comfy. All right, let's start talking about some of the clocking elements since we've talked about the lab issues. So when we want to build counters, so today and the next class will be on counters because counters are very, very important as you start to see. There are a few different ways we can build a counter on. Very often what we will do is use a T flip-flop. T flip-flops tend to be better for counters than a regular system would. So I'm going to start off with what's used for the ripple counters, which, like I said, I'm not a huge fan of, but it is a standard design and it's helpful to understand what's going on with them. So imagine I set this toggle to 1 so that it's just always going to toggle if it gets a clock impulse. And then my Q is going to be my count. And then on here, for the clock input, I put my count signal. Right? Ugly looking you. So I put my count signal into my clock. What happens then is every time I get a thing that says count, right? And the count signal will come in and I'll get a boom count for me, right? And then I'll get a bunch of don't counts. So when that happens, right, whether I do a rising edge or a falling edge, I'll only get 1 for each individual pulse of the count that comes in. So it doesn't matter if you hold it too long or don't, since it's an edge triggered, you'll only get 1 off of it. Now, what's going to come out is a sequence. Every time I see one of these pulses, this will flip. So on the short end, with just 1 bit here, I'll see a 0, and then a pulse will come in, and it'll transition to a 1. If I'm in the 0 state, it'll go to the 1 state. And then I get another pulse, and it'll go back. So every time I get a signal coming in, and if I get a 0, I stay there. So this is a very small counter, right? It's a mod 2 counter, right? Because any number mod 2 is either 0 or 1. So, but it'll count 0, 1, 0, 1. And it'll count that ad infinitum. So this is one way I can build a counter. Now let me show you why it's called a ripple counter. If I took this, imagine I wanted to go to a slightly bigger count. I go, okay, that's fun, right? What if I want to be able to count 0, 1, 2, 3? Right? A 2-bit counter. 0, 1, 1, 0, 1, 1. I'm just going to draw the arrows like this, and you can know every time there's an arrow drawn, it means that I got a pulse coming in. And I'm not going to show the stay here when the pulse isn't present. So this is just kind of a shortcut we often do when drawing these. When I look at what I need to do here, right, it's going 0, 1, right? So 0, 1, 2, 3. Well, this is my least significant bit, this one here. And it's doing that 0, 1, 0, 1 ad infinitum, exactly what this does. And then every time this is a 1 and turns off, this right here should turn on or flip. Right? Because this is on, when it turns off, this one turns on. This one is on, when it turns off, coming back to the top, this one again toggles. So that means the second bit is also a toggle flip-flop. that is set to toggle all the time, and its clock just looks at the previous bit and does it whenever it turns off. So negative edge transition. So from this combo here, we know from 1 bit, this does 0, 1, 0, 1. The second bit, we said whenever the 1 bit turns off, I want to toggle the second bit. Because the next thing is going to be 0, 0, and then 0, 1. So every time the 1 bit turns off here, I toggle the next bit. I don't do it when 0 goes to 1, only when 1 goes to 0. Does that make sense? Awesome. All right. Let's say I want to step this up to another bit. We go to 3 bits now. The next bit after this, it should wrap around again. So we notice this bit, right? So I can still keep using what I've got because I've got 2 nice little subsets of them, and they repeat perfectly in pattern. So what I have here works great for the first 2 bits. I only have to add some extra logic to handle the 3rd bit. So the niceness of this design is it's really easy to keep building each successive layer. You can go to the next one with a very simple addition. Keep what you had before, add something else on top of it. So that's the advantage of it. We'll notice the transitions happen between these units. So when this goes from both ones, right, to both zeros, it turns on, or both ones to both zeros, it turns off. So it toggles every time we see 1, 1 going to 0, 0. So now what I want to do then is just take this clock when they're both 1, I just AND them together. If they're both 1, I'm going to take that, go to my next layer. I'm going to want to toggle because it goes from 0 to 1 or 1 to 0 under that case. So that is again a toggle. You just turn it on. And again, when it goes from both on, that's what this is, both on. So when it goes from both on to both off, that's the inversion bubble on the clock. So that will cause it to, again, toggle at that event. All right. Does that make sense? Okay, awesome. Let's just add one more, right? You can imagine I've got a unit here. I might have another whole unit, 0, 0, 0, all the way to 1, 1, 1. Right? Doing that same internal pattern. The last bit is 0 for all these, 1 for all of these, and then it'll go back to 0. So again, when it's all 3 1s going to all 3 zeros, all 3 1s going to all 3 zeros, it toggles the next bit. Same thing. But I've got when I build that next unit, and this is just the efficiency part that I wanted to mention to you on this, we notice it's still a toggle. For the clocking, it'll still be when it goes from 1s to 0s, so we have the inversion bubble. When I want to add this bit onto it, I don't need to pull both of these signals down. This AND already does both of those. So all I have to do is just tap the output of that AND gate, feed it into the next AND gate. And this just adds one more layer on. And so this same pattern repeats. So you can notice, right, this is the nice thing about the ripple addition. Just like with a ripple adder, the ripple counter has a nice simple block here that you can just repeat over and over and over again. It just takes the previous clock's input and the Q output, ANDs them together, and that becomes the clock input. Previous clock's input and the Q goes into an AND gate, next clock. You can add that for as many bits as you want, and it will work. Right? I'm going to say work with a little kind of asterisk. And this is why I say work, that it's not happening all at the same time. So remember, every time I go through an AND gate, there's a delay. So imagine this thing is counting fairly slowly. It's like a human counting people coming through a turnstile or something like that. So it's a very slow system. Let's go in there. To get to this point here from that count, it's got to go through this flip-flop. It's got to go down this wire to the next one, right? So there's a time delay of one flip-flop or one stage. So this costs one stage to get to here. It's got to go through that same flip-flop and an AND gate to get to here to give the next clock. So it's two stages. To get to the next one, it's got to go through another flip-flop and another AND gate. So it's gone through three stages. Each of these stages takes time. So as you get more and more bits added on, the later bits get the signal at a bigger delay. If I'm doing something slow, like a human counting, no problems, right? So this basic design is actually identical to those mechanical hand clickers they count on. They used to also have mechanical gauges for your odometer, like the mileage counting in your car, the dash. It used to be a mechanical one. And this little trigger going to the next layer, they would have on the wheel. Right? So they would have a wheel that had the numbers on them. Right? So it'd be like 0, 1, around, eventually coming back around to 9. And there'd be a series of these wheels. They would actually have a little pin sticking out from 9 so that it would just tag the next digit in line and push it one digit further every time 9 came around. So there would be kind of like an interlock. And this 9, that would move around. It would hit the interlock that's only in one spot there, and it would move the next wheel one position going on. So that would be the way they counted. That's the same as what we're doing here. Right? This is kind of our mechanical interlock to do that. And those things work great, like mileage on a car, right? Only 1/10 of a mile. That's a long distance between them, right? Later wheels, it takes more and more of those kind of counter switches. They don't move as one smooth unit. It's kind of like you see this little kind of latency. It looks like it's twisting, and then they all even up at the end. But here's the question. What happens if this count starts getting really fast, right? Such that this count can be actually faster than the time it takes to get the signal to the last, right? So the amount of time between pulses here, if it gets on the order of how long it takes for this one to get an update because of all the latency through here, this time looks like that time. Now all of a sudden, this can get 2 pulses when this gets 1, and your count gets screwed up. That's the danger, right? So as long as you're counting a very slow phenomena, ripple counters are awesome. They're easy to build, they're easy to scale, right? If your phenomena gets fast, right, don't use a ripple counter. Ripple counters are really, really bad for that. So they're only useful for slow phenomena and not for FPGAs. You should never build a ripple counter on an FPGA. And the reason is we're using logic signals into clocks. We've already mentioned that on the first part. Logic signals can't go to clocks on FPGAs, on a standard design setups that we have now. Therefore, it will make a completely kludged together version of this, which will have bad timing and will have lots of errors, right? Which is what you encountered inside the lab. So you've seen a good example of why it doesn't work. So do not ever do these ripple type counters on FPGAs. You can do it when there's discrete components, or if you're building your own ASIC or something of that sort, but only do it if it's a slow phenomena. So if you're doing something, counting for kids' toys or mechanical counters for people at gates or things of that sort, right? This design is really easy. Away we go. Okay, do we feel good with this? Okay, I see a yes. All right, now I'm going to take this very often with this type of slow phenomena. It's something that we're going to do when we're, say, like a human being doing accounting, right? My examples like odometers and the counters at gates and things like that. People have those little hand counters. Those things are for people. This is counting in base two, but humans don't like counting in base two. So we might want to actually, instead of doing this, have a base 10 counter. But my circuits aren't base 10, so therefore I have to do binary coded decimal. I can't do regular binary numbers. I have to do BCD numbers. And this type of a sequence, I can't use exactly this for it. It's a little more complicated. So let's take a look at how we can do a ripple design for a BCD. And remember, this is just slow, not FPGA stuff. So slow, not FPGA, BCD, ripple counter. All right. The idea of a BCD counter, we need 4 digits. Is this big enough to read? Okay. Everybody can read. Good. And then it's going to return, I'm putting them in a sequence just so it's easier to see. I would actually normally encircle each of these and draw the arrows between them. Um, but I do want to have them in here because we can notice some patterns. First off, if you just look at the least significant bit, right? So this is kind of the end of the normal sequence here, right? But it does that nice 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, right? So this is toggling exactly when you would expect it to toggle. Right? There's no strangeness to its pattern at all. Right? If you look at the next one that's in here, right? I've got my zeros, my ones, zeros, ones, zeros, zeros. So it does something weird here. So this is kind of weird. Because I do have a case where I'm at a 0, I get a 1, it transitions down, and it goes to a 0. So this one has something odd. I'm going to have to do something different there. How about the next one? When both of these are 1, it should transition. So I do. Both of these are 1, it transitions. Those are the only 2 spots. So this one is completely normal from what we built before. And the last one, it transitions here when they're all 1, but it also transitions off at this. So this one is also kind of a special little case. Um, so those are my kind of 2 special cases that are going on. That means I can take these and I can just do the first and the third, I can do by toggle flip-flops. Now, I'm going to do my toggle flip-flop a little bit odd. And then I'm going to make a JK. And the reason I'm going to do JKs is because I'm going to need a JK for the most significant bit and this second bit that's in. And since I'm going to need JKs there, it's just easier to build all JKs. Often with JKs, we put the clock between J and K, just so it's easier to separate. Now, for a JK, if I just want to toggle, I set them both to 1. So these two, I'm just going to set both of them to 1 because they need to do their normal toggling. All right. Let me do this one here because it's kind of the easy first case to deal with. May not look like it's as easy as, but it is actually a quite simple case. When both of these are 1, I need it to transition to a 0, 1. In any other case, right, I'm going to be going to zeros, right? That's the only time it turns on. So when there's 2 1s here, this will turn on when this one transitions from a 1 to a 0. So both on, and this goes from a 1 to a 0. This goes from a 0 to a 1. So that suggests that this least significant bit should be the one that's determining when I do the flip, and this one should be doing the enable. So again, if I do that, this goes from a 1 to a 0. I want that to stay a 0. When this one goes from a 1 to a 0, I want that to be a 0. 1 to a 0, it should be a 0. 1 to a 0, it should go to a 0. So notice the only time I want to go to a 1 is right here. So that means when both of these are 1, I want it to be set. And any other cases, I want to reset. Well, how can we do that with a JK? Let's just take a look at the JK chart for a sec. And this does hold, and this does a reset, and this does a set, and this does the toggle or flip. Yeah, I was going at flip. I'll keep with flip. Okay, so I want a simple pattern for this that, I get, let me not just go on set and reset because that's their names here. When both of these are 1, I want to get a 1. Well, the 2 ways I can do that is either of these 2. Now, I'm not going to use my normal excitation table here because I'm kind of doing a human observation. I want this one. The other cases when I get this, so this right here, right, this transition flip means take the clock down. This transition, this I need for that spot when the previous 2 are 1, 1. In all other combinations of the previous 2, I want to go to 0. Now, in some cases, like here, that means hold. But in some cases, it means to flip. So I don't want to use hold or flip because it means one or the other. But reset always gives me a 0. So I want to use reset for the other one. Now, since I want reset for the other one, I'm going to pick flip to be the one that puts my 1 in because they both share a 1 on K. Since they both share a 1 on K, I can just do that. It makes my life really easy for my logic. Right? So I don't pick this just so I can have both of these ones have K. And then I notice J is either a 0 or a 1, which is the same as what if I ANDed these 2 bits together? 1 and 1 would give me a 1 coming in. In all other cases, when the transitions happen, I don't have both 1s, which means I get a 0. So my J value, I'm going to take the previous 2 Qs. So this is my least, this is my most. I take the previous 2 values of Q, and them together and I put them into the J. Right? That matches my observation. When they're both 1, I'll get a 1, because when they're both 1, I'll get a 1 here. 1, 1 gives me a flip, and it'll turn the 0 into a 1. Every other case, that AND gate is going to be a 0, which means I'll get a reset, so it'll just force it to be 0. Therefore, I don't care when it's happening. Right? This one will cause this column to be produced, as long as I produce this sequence. So that means I need this to come in for my count. For this one, I needed the previous Q's value come into the clock. Remember, we said this one was normal. This was one normal, and this one was normal. This and this was strange. We just built this one nicely. But the normal for this one is that whenever I get a 1 here, it's going to toggle. Right? A 1 goes to a 0, a toggle. A 1 goes to a 0, a toggle. The only time I get 1's going to 0. So this correctly built. So I've actually got 3 of my bits done. I only have to deal with this one last kind of special case. And it looks pretty normal, right? Repeat block, repeat block. The only time it's different is I don't go to a 1 here, I go to a 0. So that means that whenever this is 0, this is counting normally. When it's a 1, I need to make sure I reset this. I clear it out, which suggests again I can do this same type of a trick. And what I want on this one is this, I need to take a look and say, hey, look, count normal when this goes in, right? So when I get the normal, I've got my 1 from the previous column comes in. I want to toggle as long as that is a 0. That means I've got this K. I can do the same flip trick, right? And reset, I get an extra 0. So I'm going to use this same thing. I'm going to set K to be 1. But now the condition of what is my J01? Well, the J01 in this case, I want it to toggle as long as the most significant bit is 0. So I'm going to take Q prime. Remember, we can have both of them. You can also take this and run it into a NOT gate. I'm going to take my Q prime. I'm going to run it into J. Now, whenever Q is a 1, that means that Q prime will be a 0. So in this case, Q prime is a 0, which means J is a 0, and it'll reset that bit. Whenever Q is a 0, Q prime will be a 1, and that means I'll have 2 1s coming in here, and it'll flip, which does the normal operation. Right? So once I've got this one working, it's then very easy to make that special case. And that's really all I'm doing here is this design is saying, hey, a special case, when this one is on, I want you to do something different. But when it's off, just run normally. Does that make sense? Mm-hmm. Okay. So now we've got kind of this one. And you can actually stack this. This makes 1 digit inside of your system. And I can take the output from this one. Whenever this last bit transitions from a 1 to a 0, I know my decade finished, so I should increment to the less. So all I have to do is take this last bit. This is also the signal to the next bit. This again, if you notice, I've got logic coming in here, so it'll ripple, it'll have skew to it. And that means this output signal has to go through 4 of these blocks with some feedback, right? This is slow. So as long as it is a slow signal, you're good. If you get to a fast signal, this is doomed to fail. Okay. But it's a quick, easy way. There are a lot of slow signals out there. There's no reason not to take advantage of a nice design if you're building individual components for a slow, not FPGA system. Okay. If we're good with this, I'm going to move from ripple counters to synchronous counters. So we good? Yes, I am seeing yeses. All right. Okay. To do a synchronous counter, right? Synchronous literally means syn with Chronos clock, with a clock. So we're building a system that's going to have the clock, and that clock is just going to run into our clock signals. So we are now going to just always have that clock. We have to consider our count, and we can't use the clock as the signal to do the counting. So we're going to count without the clock. So we're going to do a standard binary count now. Okay, so this is my sequence inside of here. And again, if you want to think of this, this is 0, 1, 2, 3. We kind of draw it in a picture as 0 goes to 1, goes to 2, so on and so forth. This is just a ring going around. For the last one, 15 comes back up to 0. So this is a mod 16 counter. And we will usually call these counters, we almost always do mod them, right? Mod is your remainder. So classically we do percent as that symbol in like C or C++. So if we do some, X mod some other number, right? Whatever I want here, this one, we're doing mod 16. It'll give me a result between 0 and 15. That's why we call them mod counters. And the number that it's mod is how many in the sequence. All right. When we look at each one of these, right, we've got a couple ways we can do this. We can build a logic gate that's coming on, right? We can build it, we can use toggle gates to toggle them. But this time we would need to, instead of using the clock to toggle things, we'd have to be able to toggle based on the input itself. So I could take a look at, for instance, let's just consider the first bit. It goes 0, 1, 0, 1. If I've got the clock reading, I'm not going to put a wire if it's using the actual clock. Because otherwise, in this small board, it's just going to get really, really ugly, and I don't want to make it ugly. So imagine I've got a T flip-flop, right? And I take this and I can run it into a clock or a count signal. So if I take a count as my signal coming in and I run it into the T, if you're not counting, so no count, no count. So this is the count signal, right? You give me a count pulse. Now, the thing you have to be careful with this count pulse is if you hold this count pulse for a while, you'll get a bunch of counts. As soon as this is high, it will do a count. So you have to measure these off of our clock. So if this is count, the clock signal coming in, let's assume I'm dealing with a negative edge clock because that's common, means it'll measure it at each of these time periods. So it'll say, oh, don't count, do count, don't count. So therefore, as long as this is a short pulse that you set up, that count will work perfectly fine, right? It'll see a count pulse and it'll count. It'll wait a while. Whenever you send it the next count pulse, whenever it's 1, when this is on, it'll do the next transition. So this will still give me that same type of a counting pulse behavior. I just have to be careful that I don't make this count hold too long unless I really mean it. This is sometimes called running your counter. If I have a really long count pulse that's in, I can really, really kill the system because I just meant to do 1, but the person's like, right? They push really slowly. It'll just run like crazy, right, when this is happening. And you might not have meant that. Now, one way you can handle that, we won't build it here, but it's not a difficult one to imagine. Imagine I had a really slow fingered person, right? Or a slow fingered system, right? Maybe it's coming out of a system that has a much slower clock. If I only wanted to get 1 pulse out of this, I could do what's called an edge detector. So I can look for the pattern on the input that's a 0 to a 1. And whenever that happens, I want to cause a single pulse to go up during my clock. So if I just look for the 0 to 1 transitions, I get a 1 here. Since I don't see a 0 to 1 anywhere else, I don't get it. Right? So this is sometimes called a positive slope indicator. It can sometimes be called a positive edge indicator. It's really easy to build a simple version of this where all you have to do, you have your input, this original signal here coming in, my slow count. I run it into a D flip-flop. And I compare, right? So this has some latency. So in here is whatever it was last time period. And this one, so this is last. And this one, there's no delay, so it's the current. The clock on this is whatever clock you want to go to. So this will end up being a single pulse. And if the last one is a 0 and the current one is a 1, then I want it to work. So if the last is a 0 and the current one is a 1, I want that and, right? So last, I negate it, right? So if the last one was low, current one is high. You can also do the same thing by taking the Q prime output and running it in. That becomes last prime and current. Either way, into the AND gate, this output signal is this. And it's automatically clocked to be the right period, so you only get 1 period pulse. The book doesn't mention this, but it's a simple enough circuit to kind of understand. As long as you've got a slow signal and you want to convert it to a smaller one, it's really easy to do it. And just make sure this clock is the same as whatever you're measuring on. Then the output will never be longer than 1 clock pulse, and you won't get clock run because of this, or counter run, I should say. All right, does this little side note make sense? Slow delays on people. Okay. So again, this is also, I realize it's after lunchtime period for probably a lot of people. I also want to make sure as I'm kind of talking about these, it's really easy on a long meeting like this, particularly when you can't see and interact, to kind of lose focus. So I don't want, I, hey, I admit, if I was on your side, I'd probably have some nice tasty food and I'd be like dozing off myself. So that's part of the reason for the check back in. Um, hey, that sounds tasty. Um, but you know, I am trying to give you some stuff, particularly some stuff beyond what the book does, because when you go out as an engineer, there's kind of like the minimum basic knowledge you need, and then there's kind of what you're going to need to be a good engineer working in the field. And I don't want you to just know the minimums of what a book tells you. I want you to know the important areas. Hey, what happens if something screwy is going on? How do you debug it? And this is some of the stuff you encounter inside the labs. That there's um, these areas where there's some kind of difficulties and some subtleties, and sometimes we put them in deliberately, and sometimes like in the one you just dealt with, we actually, that did come up in, I think it was the last time, but we forgot to update the lab report. um, it just happens that sometimes mistakes come in. So if you're aware of different solutions, what causes the problems and what are the solutions. If you know what the problem, what could cause it, you can narrow down your search for the problem inside your code. So it makes you faster to debug, and it lets you know, oh, if that's the problem, that tells you what you can do to fix it. You remove that section that has the problematic areas. Uh, if you know on this one, oh, it can run easy, and you run into that running, you go, oh, I got this slow pulse. How do I convert it? Oh, yeah, right? I can do one of these edge detection techniques. Very easy to build. I mean, it's a stupidly simple circuit, but if you just saw this question, it could very easily be difficult to do. So that's why I want to, if you've seen it before, you're more likely to remember, oh, I remember that. And then you can look back in your notes or search for it on Google or whatever else, and you're likely to find it. Okay. So now we feel comfortable. I'm going to assume from now on that that count is a perfect count signal, because I showed you ways I can make it perfect if it wasn't to start with, which means I'm only going to get a count when I want to get a count. So I'm going to use this count signal coming into the T as if it is an enable signal, right? Because if this count is a 0, it won't count. So it'll only count if the enable is high. So I've got to make sure when I do want to count, I need to make sure that T becomes a 1. And that's going to be the challenge for each one of these. So I want this to count every single time period a count signal comes in. I want this next one down here and it's going to just be hooked up to the clock just like everybody else. Maybe I'll just draw a line to go into my clock. Right, so I know it's synchronous because each of these are hooked to the same clock. I only want to do the count transition whenever it goes 1 to 0. Right? So that means I'm only going to look for a count pulse, right? When both of these, right? When this one is a 1 and becomes a 0. So now if this is only a 1 for one time period. So imagine I did this. At this time instant, this toggle is turned off, right? Because it's 0 right? On that bit. Therefore, this is a 0, so this doesn't change. When this becomes a 1, it's just, this happens at the clock pulse. So this is after the clock pulse. It takes a little time to come down. So this won't get turned on till after the clock pulse. And it'll be there at the next clock pulse where this one will then toggle. And this one will turn low and it'll go off. So this feeding the next one down will perfectly handle that situation. Right. Does that transition make sense? Yes. Awesome. Um, Now let's take a look for our next. Now, actually, I should make one more category, right? I want this to go from a 1 to a 0 or a 0 to a 1. I want to count. But what if there was a bunch? So I'm going to have to, well, what if there was a bunch of held states? What if count was not on when this came in? All right. If I'm counting as fast as the clock goes, this will work. But what happens if I'm not counting as fast as the clock? What if at this time period, when I get right here, what if count turned off so that there's a whole bunch of 0011s that are supposed to stay in here? Well, the clock pulses are still coming, and it's going to see that one there, so this one will be toggling like crazy. So while this will do the transition as long as everything's going fast, it won't handle in between delays. So I need more than just this count, which will enforce the technical table. I need to also say count has to be high. I'm going to modify my drawing slightly to now account for this extra state. So if this one is true and that one is true, so it is a 1, and I am telling it to count. So I know it's a transition time. If both of those are true, now I want to toggle. All right. So we add this extra one in here because without this, these later digits are going to just run as fast as they can. If you want that, then that's awesome, right? You just put the synchronous thing, you put a 1 in on that T and let it go, right? But if you want to have a slower count, you need to say it's at the point where it should increment, and I do want it to increment. Right? So does that extra addition make sense? Now, if you notice this, I'm doing a lot of these counters kind of in sort of a human thinking through it logic sort of a way. Now, you might ask yourself the question, well, why don't we just, do a drawing for this, right? Why don't we put in a Carnot map or do one of our other designs? You absolutely can do that, right? And all you'd have to do, in addition to the possible states here, I just have to add count. That would give me, that's my input signal. So then I'd have 5 signals, 4 states plus one of those. I can make a 5 variable Carnot map. I could do the encirclements, and I would get that AND gate for the T flip-flop. I just have to do the T flip-flop excitation table to make the Carnot map. I could do the encirclements. It will reduce to that nice little AND gate. And one thing you could look at that, you could say, well, hey, I could do that. Well, the reason I don't is because 5 variable Carnot maps, are ugly and it won't fit on my board, right? Because that's, I guess it would, but it would be very hard to read 2 tables written like that with zeros and ones in them and trying to do an encirclement between these 2 stacked. All right, so that's one. Now you could do it on your own. No disagreements with it. That's just not necessarily the prettiest. Could I do a Mux design? I could. Again, Mux designs are nice and elegant, but then I'd have a multiplexer at each one of these. And it turns out it's a much simpler circuit for that. So while Mux design would work, Mux design is like using the old expression, using a sledgehammer to try to swat a fly, right? Actually, a sledgehammer wouldn't swat a fly. So maybe, I don't know, using a nuclear bomb to take out a fly. Right? It is massively more powerful than you need. A nuclear bomb will certainly kill a fly in that area, but it's just a, a completely inefficient use of things, right? It's a waste, and as engineers, we hate that. Um, so there's another level, and this is kind of so you could go through all the techniques. Any of the techniques would work. They wouldn't necessarily give you this nice, simple design. K-maps would, right? The K-map absolutely would work. It's big and ugly, but it works. I mean, K-map is always a safe way to go, but as it gets too big, it can become cumbersome, right? And there's versions of it, Quine-McCluskey, that does it algebraically, and a computer can solve it for you. But as that gets bigger, this is a good time to just mention one of the big problems that's out there. You might just say, well, hey, why don't I just always implement Quine-McCluskey? Well, it turns out Quine-McCluskey is slow. Um, that's you got to kind of quantify this. What I mean by slow. So slow for a computer algorithm means that we don't have any known way to calculate this in what's called polynomial time. So if in this case, the number of inputs, right? There's 4 states plus 1 input. So or the number of variables, there's 5 variables. So I would say it's 5. If my algorithm took polynomial time, it could be like 5 squared, or it could be like 5 cubed, or something of that sort. If it's polynomial, this number is fixed, I'm still going to end up with a reasonable type of a behavior. But a non-polynomial thing looks more like something like some time to calculate to the number of variables power, right? So if instead of having my 5 down here, my variables is in the exponent, right? So it's an exponential time. As these variables grow, no matter what this time is here, this is going to get ridiculous. T to the 5th versus T to the 6th is a huge difference. And it doesn't take very long before you end up, making something that's completely unreasonable. So even just addition for a modern computer, you've got two 64-bit numbers added together. T to the 128 is ludicrous, whereas like 128 squared or 128 cubed is not that bad. So the difference between a polynomial, right, and something that is not a polynomial is gigantic. So we really want things that are polynomial. We generally classify these as kind of reasonable to calculate, and these as just too darn slow to calculate. And it turns out that amongst the just too darn slow to calculate ones, unfortunately, Quine-McCluskey is one of them. So we haven't proven that there's not a fast algorithm to do this, but nobody's been able to find one. So this is one of the great open problems in our field today is, how do you handle these kind of slower algorithms? It's sometimes called the P versus NP problem, polynomial versus non-deterministic polynomial. So it turns out all those things that are not polynomial can be calculated with what's called a non-deterministic polynomial. I can do it in polynomial time if you give me a non-deterministic Turing machine. A non-deterministic Turing machine can just guess, and then you can check the answer in polynomial time. That's what it means. So it turns out that it's just really hard for the best methods to work. So another thing that's out there that often gets disregarded is you're getting familiar with this. As a human being, you can look for patterns and understand them. So as a human, I can actually find some of these and then verify them quickly that they do in fact work. And computers can verify a design you come up with very, very quickly. They just can't generate them quickly. So this is something you're good at. And so I'm walking you through how I'm kind of coming up with these so that you can do the same thing. All right. We've got up to the second one transitioning. All right. To get to the third one, I want both of these on, and it had better be a count to toggle the next one. Both ones on and the count happens, it toggles. Both ones on and the count comes in, it toggles. So this one needs both of these on and So this one, that one. That's my first and. Here's my second. So I feed them back together and put that into toggle. Okay. To go to the next one, I need all of them on and the count, and then it toggles. All of them on and the count, and it toggles. I can then just, for the next one, toggle Q. And we again get a very nice, pretty answer. And it'll keep counting. Now, this works great. It's easy to design. The problem is this count line, right? 1 gate, 2 gates, 3 gates. This latency gets bigger and bigger. Right? Now I can remove that by just redoing all the AND gates together. I can run all of the previous queues together into a series of different AND gates so that I don't have to wait for any one AND gate to produce an answer. But then the number of inputs increases. So there's practical limits to these synchronous ones based on how big these go and how long the latency is. These AND gates. So if the number of AND gates gets too large, so one efficient way is what's doing block versions of these. I just take the number of these, I cascade them like this. When it gets too slow, I do a single gate that takes all the previous ones. And that way I can kind of get a quicker answer to it. Various speedups without necessarily having to have lots of different AND gates in between. But this design will work. Eventually it will get too slow on the latency to meet the clocking constraint. Then you have to go to wider gates where you smush a couple together. But essentially that is the design. Do we feel good with this? Okay. We have hit our time. So I'm going to stop us at this point. We will do a base 10 version of this, a BCD next time, and then we'll look at a couple other kind of specialized counters and some other issues with counting, and that'll kind of round us out for counting. Any questions before we go? All right, well, seeing no questions, I wish you all a good day, and watch a little bit later today for the midterm stuff to pop up, and there should virtual thumbs up. Cool, thank you. And I should have the homework also available later today. So those two ones should be up there, and otherwise we should be good. I wish you all a great day. Miss you all. Hope you're staying healthy, and hopefully I'll see most of you sometime in the fall. Hopefully we won't have a giant relapse of this. I see a question mark. When should you have the corrections done by? I'm going to be kind of honestly very relaxed with this because as long as I get it in time to turn the grades in, I'll be good with it. You're under a lot of time constraints. I'm under weird constraints. We're at a very odd time in the world, so I'll take them when I get them. I think that's just fair. Any other questions? You are welcome very much. Have a great day, everybody, then. Stay safe. God bless.